if the most famous dying star in our galaxy isn't just boiling itself to death, but is actually being carved open by something lurking in the dark. For centuries, we assumed the relentless 6-year pulsing of Betelgeuse was just internal instability, but in 2025, astronomers using the Gemini North telescope realized we were completely wrong. Betelgeuse is not pulsing alone. It has a passenger, a hidden companion star, orbits so close it physically plows through the giant's outer atmosphere, acting like a cosmic snowplow clearing dust every 2,190 days. We call it Siwarha, or the Beetle Buddy, and its existence forces us to rewrite everything we thought we knew about how red supergiants die. If you want to track these deep space anomalies with me, click subscribe and join our investigation. Just as 3I Atlas reveals the chemistry of a foreign system from its recent perihelion passage, this hidden companion is the key to understanding how stars themselves live and change. You all track the carbon depletion signatures Atlas gave off when it whipped past our Sun last December. You know how a single foreign object changes our understanding of local physics. Siwarha does the exact same thing for stellar evolution, but on a scale that defies common sense. We need to talk about the long secondary period. Astronomers noticed long ago that Betelgeuse has two distinct beats, a fast 400-day pulse and a slow, lumbering 2,190-day cycle. Everyone chalked the long cycle up to internal convection, giant plumes of plasma rising from the core, boiling off into space. Makes sense. A star with a radius stretching out past the orbit of Jupiter is going to boil. But here is the thing. Convection models never actually fit the light curve. The math always broke down. The dimming was too regular, too mechanical. Last year, a team pulled decades of archival data and combined it with fresh, high-resolution observations from the Gemini North Observatory in Hawaii. They did not just look at the visible light coming from the star. They tracked the radial velocity. They measured exactly how fast the surface of the star wobbles toward and away from Earth. And they found a distinct gravitational tug, a mass pulling the center of Betelgeuse off its axis by exactly 1.3 miles per second. Every 6 years, you do not get a mechanical 1.3 mile per second wobble from a plasma plume. You get it from a massive, solid gravitational anchor. Wait, let me clarify. Not solid like a planet. A star, a distinct secondary star with 1.2 times the mass of our own Sun. Betelgeuse weighs in at roughly 15 to 19 solar masses. Siwarha is 1.2 solar masses. Picture a 400-seat theater. Betelgeuse is the entire building. Siwarha is a single chair sitting in the lobby. Yet that single chair dictates the lighting for the entire block. How does a star that small control the light of a giant? It comes down to the bizarre physical environment it occupies. Let me back up. Betelgeuse does not have a hard surface. Red supergiants bleed their mass into space constantly. The star sheds roughly 1 Earth mass of gas and dust every single year. This creates an extended, chaotic atmosphere, a thick, opaque shell of titanium oxide and silicate dust expanding outward for billions of miles. Siwara orbits inside this exact shell. Its orbital distance is roughly twice the distance from the Earth to the Sun. Around 186 million miles from the core of Betelgeuse. So, what happens when a young, hot star plows through an ocean of heavy, cold dust at 30 miles per second? It creates a wake, a literal gap in the medium. The companion star emits intense ultraviolet radiation. As it moves through the dust shell, that radiation hits the surrounding silicate particles. The ultraviolet light carries momentum. It heats the dust grains past 1,500 degrees Fahrenheit. It pushes them. It vaporizes them back into an invisible gas. It clears a massive transparent channel through the cloud. From our vantage point on Earth, we look through this channel. When Siwarha swings around to the side of Betelgeuse facing us, it blasts away the obscuring dust in our line of sight. Suddenly, we see the blazing hot lower layers of the red giant clearly. The entire system brightens. Then, as the companion continues its orbit to the far side of the giant, the dust cools and collapses back in behind it. The window closes. The system dims. The 6-year cycle is not the star expanding and contracting. It is a lighthouse beam created by a cosmic snowplow. Let us dig into the raw data from Gemini North. You do not just point a telescope at Betelgeuse and see a tiny second star. Betelgeuse is 100,000 times brighter than our Sun. Siwarha is a fraction of that brightness. Finding it is like trying to spot a specific firefly hovering next to a military searchlight while standing 500 miles away. The glare washes out everything. So the team in 2025 used speckle imaging. Earth's atmosphere is a chaotic mess of hot and cold air pockets. These pockets act like moving lenses, blurring the light of distant stars. To beat the blur, the Gemini camera takes thousands of incredibly fast snapshots, 10-millisecond exposures. By doing this, they freeze the atmospheric turbulence. They stack these frozen frames in a computer. They run complex Fourier transforms to convert the images into spatial frequency maps. They mathematically subtract the primary star's overwhelming halo. And hidden in the mathematical noise of those stacked frames, the signature of the companion finally emerged. Look, astronomers have suspected a companion for over 50 years. I remember reading papers back in the 1980s about a weird bump in the ultraviolet spectrum of the star, a slight asymmetry in the radio emissions. But the evidence was always circumstantial. The 2025 data locked it down because it matched the radial velocity timeline perfectly. They also measured the orbital eccentricity. It is not a perfect circle. The orbit is highly elliptical. It has an eccentricity of 0.6. That means the companion spends part of its 2,190-day orbit plunging deep into the dense inner chromosphere of Betelgeuse, and the other half swinging out into the thinner, cooler dust shell. Every time it dives in, the friction generates an immense shock wave. The gas piles up in front of the companion, compressing and heating until it glows in the extreme ultraviolet. We completely missed this shock wave for decades because the dust shell absorbs extreme ultraviolet light and re-emits it as diffuse infrared heat. It masked the violence of the orbit. I am curious how you interpret this data. We have a 1.2 solar mass star orbiting deep within the ejecta of a dying giant. Does it accrete that material and grow rapidly? Or does the radiation pressure from the giant strip it bare before it can consume anything? Leave a comment below with your thoughts. I read all of them. This brings us to a massive problem, the timeline. Betelgeuse is roughly 10 million years old. It is dying because massive stars burn through their core hydrogen reserves in the blink of an eye. They live fast and die young. Siwarha, at one point, 2 solar masses, should be a main sequence star. A star slightly heavier than our Sun lives for about 5 billion years. So we have an infant star paired with a dying behemoth. How did they pair up? You have 2 options. Option 1. They formed together from the same molecular cloud 10 million years ago. If so, Siwara has barely started its life. It is still settling into its core hydrogen-burning phase. Meanwhile, its brother has already exhausted its core, ballooned into a red giant, and is preparing to detonate. Option 2. Betelgeuse captured Siwarha. A rogue star wandering through the Orion OB-1 stellar association drifted too close. The gravitational well of the massive giant snatched it. Wait, think about the mechanics of a capture. It requires a massive transfer of kinetic energy. If a star just flies by, it gains speed as it falls into the gravity well and uses that exact same speed to escape out the other side. To stay, it has to hit something. It has to experience drag. What if Siwara slammed into the outer dust shell of Betelgeuse thousands of years ago? The friction of that dust cloud bled off its momentum. It spiraled in, and now it is trapped. Imagine the physical environment 186 million miles from the center of Betelgeuse. The temperature of the gas there sits at roughly 2,500 degrees Fahrenheit. The density is a vacuum by Earth standards, but for a stellar environment, it is thick, heavy with neutral iron, magnesium, and silicon. Siwarha plows through this material. As it does, its own gravity pulls that gas down onto its surface. It accretes mass. We can calculate the accretion rate. Siwarha sweeps up roughly 1/10 billionth of a solar mass every single year. That sounds insignificant, but over the next 100,000 years, that material accumulates. It builds a massive accretion disk around the smaller star. The friction inside that disk generates intense X-ray emissions. The gas moves so fast it rips electrons from their nuclei. We should be able to see those X-rays from Earth, and yet the Chandra X-ray Observatory data from the early 2020s showed Betelgeuse to be surprisingly quiet in the X-ray spectrum. Why the silence? The dust shell is just too thick. The X-rays are absorbed by the surrounding titanium oxide before they ever escape the system. The giant is swallowing the screams of its companion. The math does not lie. The companion is there, but the silence is deafening. Truly. We need to draw a clear line between the Great Dimming and this 6-year cycle. They are entirely different mechanisms. In late 2019, Betelgeuse dropped by 1.2 visual magnitudes. It was so dim you could barely find it in the Orion constellation with the naked eye. That was a localized surface mass ejection. The star coughed out a 400 billion-ton piece of its photosphere. That plasma cooled into a localized dust cloud directly in our line of sight. But that was a one-off event. It was chaotic. The 6-year cycle is clockwork. The 2025 Gemini data proved that the Great Dimming obscured the companion cycle for a few years, throwing our models into total chaos. When the dust from the 2019 ejection finally cleared late last year, the 2190-day pulse was right back on schedule. The companion had not missed a beat. It just kept carving its path through the debris. How does radiation physically push dust? It is about momentum transfer. Photons have no mass, but they have momentum. When an ultraviolet photon from Siwarha hits a grain of silicate dust measuring exactly 0.1 microns across, it transfers that momentum. It pushes the grain. Now multiply that by 10 to the 45th photons per second. The radiation pressure creates a cavity, a bubble measuring 400 million miles across. As the companion orbits, it drags this 400 million mile bubble of clear space with it. Which is strange, because a bubble that size should distort the overall shape of the star's emission. We should see a lopsided infrared signature. And last year, the James Webb Space Telescope looked closely at the mid-infrared spectrum of the system. It found a distinct asymmetry in the dust shell, a hollowed-out region trailing behind the calculated position of the companion, the physical footprint of the snowplow. I mentioned Atlas earlier. You remember how the telemetry from its coma showed a complete absence of diatomic carbon. That told us the comet formed in a carbon-poor region of its native star system. It gave us the chemistry of a place we will never visit. Siwarha is doing the exact same thing for the interior of a dying star. By clearing that 2190-day window in the dust, it allows our spectroscopes to look directly at the lower photosphere of Betelgeuse. It peels back the obscuring layers. When the window opens, we see the chemical factories at work. We see the exact isotopic ratios of oxygen and carbon being forged just above the core. We see the convection cells bubbling up material that has been fused deep inside the nuclear furnace. Without Siwarha clearing the path, that data is permanently blocked by the outer dust shell. The companion is a lens, a heavy, violent lens. Let us look at the broader implications. Betelgeuse is not the only red giant with a long secondary period. Astronomers have cataloged thousands of them. Antares in the constellation Scorpius does exactly the same thing. It has a fast pulse and a slow, multi-year dimming phase. For decades, the astrophysical community tried to force-fit convection models onto all of them. The 2025 discovery breaks that paradigm entirely. If Betelgeuse has a companion driving its long cycle, maybe they all do. Think about that for a second. We might be looking at a universal mechanism. Maybe the only way a star can grow to the size of a red supergiant without tearing itself apart is if it has a smaller companion acting as a gravitational whisk, stirring the outer envelope and regulating the dust production. The companion prevents the dust from choking off the star's radiation. It creates an exhaust port. Anyway, the most fascinating part of this dynamic is not the past, it is the future. Consider the endgame. Betelgeuse is going to explode, not millions of years from now. Soon, astronomically speaking. Sometime within the next 100,000 years, the nuclear fusion in its core will hit iron. Iron takes more energy to fuse than it releases. The outward pressure of fusion will stop. Gravity will win. The entire 600 million mile wide star will collapse inward at a quarter of the speed of light. It will hit the dense iron core and bounce outward. It will trigger a Type II supernova. Where is Siwarha when that happens? Sitting right in the line of fire, just 186 million miles away. Light takes about 16 minutes to travel from the core of Betelgeuse to the orbit of Siwarha. The shock wave will travel slower. The shock wave will take just over 2 hours to reach the companion. For 2 hours, Siwarha will sit there, oblivious to the fact that the star next to it has ceased to exist. Then the wave hits, a wall of neutrino-driven plasma carrying the energy of 1 billion suns. What happens to a 1.2 solar mass star when it takes a supernova to the face at point-blank range? It does not vaporize. Stars are incredibly dense. The shock wave will instantly strip away Siwarha's outer atmosphere. It will blast away the accretion disk it spent thousands of years building. The extreme heat and pressure will inject radioactive isotopes directly into the remaining layers of the companion. Elements like nickel-56 and titanium-44 will be driven deep into its photosphere, and the sheer kinetic impact will impart a massive kick. Wait, I just said massive kick. Let us be precise. The shock wave will inject over 10 to the 41st ergs of kinetic energy into the companion. That is enough to accelerate a mass of 2.4 octillion tons from its current orbital speed of 30 miles per second to over 400 miles per second. Right now, Siwarha is gravitationally tethered to a 15 solar mass anchor. The supernova explosion will shatter that binding. Betelgeuse will lose 80% of its mass in a single day, blowing it out into the interstellar medium. The central anchor will simply disappear, leaving behind a tiny 12-mile-wide neutron star. With the gravity gone, Siwarha will fly off in a straight line. It will become a hypervelocity star, a rogue, shooting across the Orion constellation like a bullet, carrying the chemical scars of the supernova embedded in its skin. Millions of years from now, astronomers in some other star system might detect Siwarha flying through their neighborhood. They will analyze its spectrum. They will see the titanium-44 anomaly, and they will know it survived the death of a giant. This is how the universe distributes complex chemistry. It is a violent, interconnected machine. Let us return to the present data. The 2025 discovery relied heavily on analyzing the exact timing of the dimming events. The researchers noticed a slight phase shift. The 2,190-day cycle was not perfectly static. It was drifting by about 3 days per century. Why would the orbit drift? Because Betelgeuse is losing mass. As the giant bleeds a millionth of a solar mass into space every year, its gravitational pull weakens slightly. As the gravity weakens, Siwarha's orbit widens. It spirals outward by a few inches every single orbit. It is a microscopic change, but over centuries it adds up to a measurable phase shift in the light curve. We can literally watch the gravitational bond between the two stars decaying in real time. The precision required to measure a 3-day shift across a century of archival observations is staggering. They used glass photographic plates from the early 1900s. They digitized them. they measured the exact diameter of the exposed silver grains on the glass to determine the historical brightness of the star. They fed that data into the modern models alongside the Gemini North radial velocity sweeps. They built a timeline. In the 1920s, the dimming hit its minimum in January. By the 1980s, the minimum had shifted to February. By last year, it shifted again. The mechanical perfection of this shift rules out internal convection entirely. Plasma plumes do not drift by exactly 3 days per century. Orbits do. We are witnessing a dance of stellar decay. Let me explain exactly how the companion impacts the surface of the giant during its close approach. Because the orbit is highly elliptical, the distance between the two stars changes dramatically. At Apastron, its furthest point, Siwarha is out in the cold dust. At Periastron, its closest approach, it dives to within 130 million miles of the core. It grazes the top of the convective cells. When it gets that close, its gravity pulls on the plasma of Betelgeuse. It raises a tidal bulge. Just like the moon raises tides on Earth's oceans, Siwarha raises a tide of superheated gas on the surface of the red giant. A mountain of plasma measuring 5 million miles high follows the companion as it races across the star's face. This tidal bulge changes the surface temperature of the giant. The gas in the bulge expands, and as it expands, it cools. It drops from 6,000 degrees Fahrenheit to 5,500 degrees. This cooling triggers a rapid condensation event. The cooler gas immediately forms fresh titanium oxide dust right on the surface of the star. So the companion is doing two things at once. On one side of its orbit, its radiation clears the old dust away. On the other side of its orbit, its gravity triggers the formation of new dust. It is an engine of creation and destruction, a regulator valve for the entire system. Without the 2025 data, we would still be scratching our heads, wondering why the dust production of Betelgeuse is so completely asymmetrical. The beauty of this discovery lies in its elegance. For centuries, we treated Betelgeuse as a solitary monster. We built incredibly complex mathematical models to explain its behavior. We invented new types of magnetic dynamos and bizarre convection physics to make the math work. We tried to force the star to do impossible things. But nature is usually much simpler. You drop a 1.2 solar mass weight into a dust cloud, and the physics resolve themselves. The anomalies disappear. The light curve makes sense. The radial velocity makes sense. The infrared asymmetry makes sense. It is a profound reminder that our view of the universe is severely limited by glare. We missed the second star in the Betelgeuse system for the same reason we miss so many things. The primary signal was just too loud. It takes clever engineering, like the speckle imaging used in Hawaii, to subtract the noise and find the truth hidden in the margins. We have to blind the telescope to the giant to see the companion. This changes our target list for the next decade. If speckle imaging can pull Siwarha out of the glare of Betelgeuse, what else can it find? We are currently pointing these arrays at Antares. We are looking at Ras Al-Gethi. We are looking at every red supergiant within 1,000 light years. We are looking for the telltale wobble of hidden companions. Because if this mechanism is universal, it rewrites the timeline of galactic chemical enrichment. Red supergiants are the primary factories for elements like carbon, oxygen, and nitrogen. The elements that build planets. The elements that build biology. If companions like Siwarha are regulating how these stars shed their material into the void, then these tiny hidden companions are the true architects of the interstellar medium. They control the exhaust rate of the chemical factories. I want to take a moment to look at the geometry of this system from a different angle. Imagine standing on a hypothetical planet orbiting Siwarha, a planet locked in that 2,190-day orbit. What would the sky look like? Looking toward Betelgeuse, there is no night. The red giant would fill 40% of your entire sky. A boiling, terrifying wall of crimson plasma stretching from horizon to horizon. You would see the convection cells with the naked eye, pits of darker, cooler gas the size of the Earth, bubbling up and sinking back down in a matter of weeks. The heat would be absolute. Looking away from Betelgeuse, the sky would be completely black. Not the black of empty space, the black of total obscuration. The dust shell surrounding the system is so thick it blocks all starlight from the rest of the galaxy. You would see no other stars, no Milky Way, just an endless choking wall of silicates and titanium oxide. You would be trapped in a 400 million mile bubble of clear space, caught between a wall of fire and a wall of dust, orbiting in silence until the fire finally explodes. This is not science fiction. This is the exact, measured physical reality sitting 500 light years from Earth. It was sitting there when the Egyptians built the pyramids. It was sitting there when the Aboriginal Australians first noticed the fading of the red star and wove it into their oral histories. They saw the dimming. They saw the 6-year cycle. They did not have telescopes, but they had generational patience. They watched the sky long enough to realize the star was breathing. We spent modern history trying to prove the breathing was internal. Now, thanks to the data pulled down last year, we know the breathing is external. It is a shadow play. And the implications for stellar evolution models are immediate. Every textbook that models the mass loss rate of a solitary red supergiant now needs an asterisk. We have to recalculate the lifespan of these stars based on the presence of these gravitational snowplows. A star like Betelgeuse might live an extra 100,000 years simply because the companion is efficiently stripping the insulating dust away, allowing the giant to bleed heat into space more effectively. Or it might die faster because the tidal forces from the companion are churning the core, mixing fresh hydrogen into the fusion shell and accelerating the burn rate. The astrophysics community is currently tearing itself apart, debating these two outcomes. The data from 2025 gave us the physical mechanics, but the long-term consequences are still entirely up in the air, which brings us back to the most critical point: observation. We cannot rely on old assumptions. The great dimming of 2019 taught us that massive stars can undergo catastrophic surface events that mask their underlying cycles. The recovery of the 2,190-day pulse taught us that the underlying mechanics of a star system are incredibly resilient. The companion did not care about the surface ejection, it just kept orbiting, unmoved, unstoppable. We have isolated the signal. We have calculated the mass. We have defined the orbit. We have mapped the dust cavity. We have solved the mystery of the blinking giant. But the universe does not let you close a file without opening 3 more. The origin of the companion remains unsolved. The X-ray absorption mechanics remain unsolved. The exact timeline to supernova remains unsolved. We will continue to track the radial velocity of Betelgeuse every single night. We will watch the tidal bulge rise and fall. We will watch the snowplow carve its path. If you value this kind of deep space investigation, leave a like, hit subscribe, and I will see you in the next analysis.